So we go through a lot of stuff in this class to make sure that you know how to do covalent bonding and to understand how nonmetals share electrons. But we're kind of schizophrenic in this class. And to be honest, we're schizophrenic throughout all of my chemistry education, all the way through my master's degree. And really it would have been the same way through my PhD or had I stuck around for a postdoc. We'll think about things covalently, but we'll also think about things in terms of what if the more electronegative elements completely stole electrons from the less electronegative elements. So what if this was completely ionic? What would the charges be? These will give us oxidation states or charges. So with that in mind, we can figure out, is oxygen more or less electronegative than carbon? Is chlorine more or less electronegative than carbon? And then say that these bonding electrons are actually assigned to chlorine for the purposes of assigning a charge. So it's a weird accounting system, but let's check it out. So first we go to the periodic table. Elements that are up and to the right are more electronegative than elements that are down and to the left. So fluorine, for example, is way more electronegative than francium. As it turns out, chlorine is more electronegative than carbon, but oxygen is also more electronegative than carbon. Oxygen is obvious because it's to the right. Chlorine you'd have to look up, but it's more electronegative than carbon as well. So what this means is that if you were going to look at this molecule ionically to assign a fictitious formal charge or a oxidation state to each of these elements, you could do so. And what you would do is you would say, okay, since the chlorine is more electronegative than the carbon, it would end up having these two electrons. So we would think of this as chlorine with 8 electrons around it. Actually, I have a better idea. Hang on. Let me... So we would actually think about this bond, these electrons from this bond actually being put back on chlorine. And we would think about it the same way with this bond as well. This chlorine is identical to this one. So we would think about the bonding electrons being put back on this chlorine. And for oxygen and carbon, oxygen is more electronegative. So we would think about the electrons from each of those bonds being put back on oxygen. So that was 4 bonding electrons. We'll put them all around the oxygen. So this is the covalent picture for the molecule. This is the fictitious accounting for charges version of the molecule. So the charge on this oxygen is going to be a charge that you get from having 2 more electrons than you have around a neutral oxygen. So a neutral oxygen has 6 valence electrons, right? You can always check in the periodic table. It's in this column, so it's going to have 6 valence electrons. A neutral carbon has 4 valence electrons, and a neutral chlorine has 7 valence electrons. If I look at the broken bond picture to get oxidation states, what I see here is that the oxygen has 8 valence electrons, which is 2 more than the neutral oxygen. So it has 2 more electrons. That's a 2 minus charge. Carbon, neutral carbon, has 4 valence electrons. This carbon has 0. So a deficit of 4 electrons from something that was neutral is going to give you a +4 charge. each of the chlorines, when it was neutral, had 7 valence electrons. It now has 8. So that's 1 extra electron. That's a -1 charge for each of these. So if you had to assign an oxidation state, or a formal charge, or charge, whatever you want to call it, you could say that formally there's a -1 charge on each of the chlorines, a -2 charge on the oxygen, and a +4 charge on the carbon. Overall, it has a 0 charge, right? 4 minus 1 minus 1 minus 2 is 0. That's right. Our overall molecule did have a 0 charge. And to be honest, this picture, this idea of the shared electrons, is a lot more close to real life than this picture where there's ridiculous charges on carbon. But if you are going to assign charges, formal charges, this is what you would assign. So that's kind of the method that you can use to assign an oxidation state or a formal charge to elements that are covalently bonded.